Alright, let's read what the question says. Consider the function fs defined by the following integral for positive real number s. Fs equals integral from 0 to infinity t of s minus 1 e minus t dt. And based on this, I have to answer the next 5 paths. You may answer without, showing that the above integral converges. Alright, so the first part is to find f of 1. So if I go ahead and plug that in, I'll get t of 1 minus 1, so that's 0. E of minus t dt, which is this integral, and this is a very standard integral. It results to this, and with the limits you'll get 1. So the first part was straightforward. The second part says the inequality e to the power t is greater than t to the power n over n factorial holds for any positive real number t and non-negative integer n. Then I have to prove the following inequality. Okay, so this equality they gave is integral from 0 to 1. I'll write this somewhere. Yeah. So they gave us 0 to 1 t of s minus 1 e minus t dt. And I have to compare it to something so that the following integral that results to 1 over s. Okay, so notice that e to the power t will lie from 0 to 1 for all t that's in 0 to 1, because if t is 0, then this becomes e to the power minus 0, which is 1, and when that becomes and when t becomes 1, this is e power minus 1, which is 1 over e, so that's less than 1. So it's somewhere in between 0 to 1, this e to the power minus t term. More precisely, it's in between 1 over e to 1. So the point is that it's always less than 1. So I can, if I write a new integral, which is ts minus 1, and I replace e to the minus t with 1. So then this integral is always bigger than the one on the left, because for this whole range of t, this term is bigger than this term. Alright, so I get that, and this is a very simple integral, 0 to 1 ts minus 1 dt. I can use power rule here because I think they have said that s is positive real number, so I can use the power rule here, and that will result it into being this, which is 1 over s minus 0. So I get 1 over s. So this integral is less than 1 over s, and that's what I was required to prove. So this part is done. And the part B says when n is greater than s and both are greater than 0, show that this inequality holds for any real number c greater than 1. Okay, so we have this 1 to c t s minus 1 e minus t dt. Okay, now I'll use the truncated Taylor version, e power t that's clearly greater than t to the power n over n factorial. And I say this is truncated Taylor version because you know the Taylor expansion for e, that's simply this, right? So what they've essentially given us is this same exact same series, but they've like ignored every other term except the last one. So of course this is bigger. Alright, and now if I go ahead and reciprocate both the sides, then this becomes e minus t less than n factorial over t power n. And this is true for all t, all positive t, and t is positive here because they have said 1, because they've given the limits from 1 to c and c is greater than 1, so t is always positive, so this is always true. So if I create a new integral, which is, this is the one that we have, and this is the one that I'll make, 1 to c ts minus 1 n factorial over t to the power n dt. So this term is always bigger than this term for this given limit, so the overall integral is also bigger. Alright, again n factorial here is a constant, so that goes out, and I'm left with s minus n minus 1 dt. Okay. So if I go ahead and use power rule again, I'll get n factorial times t s minus n over s minus n from c to 1, which is n factorial times s minus n c power s minus n minus 1. I'll go ahead and factor in a minus 1 to make this of the form n minus s, because that's given in the question. So it becomes n minus s, and this becomes 1 minus cs minus 1. Alright, and they have said that n is greater than s, so s minus n is negative, and they've also said c is greater than 1, so c to the power s minus n, that lies from 0 to 1. So 1 minus c raised to the power s minus n, that also lies from 0 to 1. So this whole term is lesser than n factorial over n minus s. Basically what I'm saying, that this 1 and this term is always lesser than 1, so this term is bigger than this term overall. Alright, so this is the final result that I get. I started with this integral s minus n e minus t dt, and this is what I was required to prove. So this part is done. In the third part, they're saying when the second derivative of fs is expressed as d2s over ds squared, some function of g and some function in t and s, e minus t dt, find a function g which satisfies this. You may show your answer without showing that the order of differentiation and integration can be changed. Alright, so fs is 0 to infinity 0 to infinity ts minus 1 e minus t dt, and when I try to differentiate it with respect to s, this whole term, it's a function in only t, right? There's no s here, so this is a constant when I'm differentiating, so I'll only need to differentiate this term, and that term is of the form some constant times some function in x, and I'm differentiating this with respect to x. So by simple chain rule, it's this itself times ln a times the derivative of that function. That's a simple result from power rule, so I'll use that. So this becomes the same term ln t times the derivative of s minus 1, that's 1, and the rest of the terms. This is the first derivative, and similarly second derivative, this whole term, it's a function in t, so that gets ignored again, and I do the same thing with this ts minus 1, that's ln t, and this whole term will come here, so I get 2 times ln t, so ln t squared e minus t dt, and they have said that this here is gst, so I get g of st as ts minus 1 ln t whole squared. That's the answer to the third part. In the next part, they're saying that they have defined this value d as this integral minus this integral, and I have to find this d given that this holds true. Okay, so I'll go and simplify d first. D is this integral minus this integrals squared. Alright, so if you notice that this term and this term, they actually look familiar to what we just derived. If I plug in f dash s at s equals 1, this term, it becomes t to the power 0, and I'm left with 0 to infinity ln t e minus t dt, which is what we have here. So this becomes f dash at 1. Similarly, at f double dash at 1, that becomes 0 to infinity ln t whole squared e minus t dt. So this becomes f double dash at 1. So d is basically double derivative of f at 1 minus square root of single derivative of f at 1. And they have said that the double derivative of log of f, and they have said that that's equal to pi squared by 6. So if I go ahead and write that as derivative of f of s equals pi squared over 6. This I can simplify and write that as simply using power rule, it becomes d by ds of fs times f dash s. And that's equal to pi squared by 6. And again use chain rule here. So this becomes square root of denominator times the denominator times derivative of numerator, so that's double dash s, and then subtract derivative of denominator times numerator, so that's f of 1 f dash 1 whole squared, and this is equal to pi squared by 6. Okay, and they've given that this is at s equals 1, so this is 1 everywhere. Alright, this is at s equals 1. But we have evaluated that f of 1 equals 1, so this whole thing, it's simply f double dash at 1 minus f dash 1 whole squared equals pi squared over 6. But this is exactly our d, this. So this is simply pi squared over 6. And that's the solution to the fourth part. And in the last part, they're saying that define a function PR for positive real number r and alpha in this manner, and then I have to evaluate s. Okay, so this is PR, r over alpha times e power minus r squared over 2 alpha. So PR dr becomes r over alpha e minus r squared over 2 alpha times dr. Now I'll go ahead and make this substitution. R squared equals to alpha z, so that means 2r dr becomes 2 alpha dz, or r dr is alpha dz. So r dr becomes alpha dz, so alpha dz, and I had this alpha here already, and r squared becomes 2 alpha z divided by 2 alpha, so that's just z, and this alpha cancels out, so I get e minus z dz. Okay, so I'll go ahead and write s, that was 0 to infinity, log of r PR dr, but that's e power minus z dz minus, this is squared, 0 to infinity log r e minus z dz whole squared. Alright, so I have to create, so I have to write this log r term in terms of z. So I'll go ahead and do that. R squared is equal to 2 alpha z, so r is plus minus root 2 alpha z, but they've said that r is a positive real number and so is alpha, so this can't be negative, so I'll take only the positive root. Log of r becomes log of 2 alpha z power half, and by the laws of logarithms this becomes 2 alpha z. So I'll simplify s. This term squared e minus z dz minus log of half log 2 alpha z dz, this term whole squared. So is this gonna be a lengthy calculation from here on out? I'll go ahead and do that. So this becomes 1/4 integral 0 to infinity log of 2 alpha z, that I can write as log of 2 alpha plus log z from the laws of logarithms, 2 alpha plus logarithm of z whole squared e minus z dz minus 1/4 integral log. For this as well I'll do that. By the way, I factored this half out, so it came out as 1/4 because there was a square here, right? So it came out as 1/4. Alright, I'll take the whole 1/4 out common and then expand this from a squared plus b squared plus 2ab. So that becomes log of 2 alpha squared plus log of z squared plus 2 log 2 alpha times log z. So that becomes log 2 alpha log 2z times e minus z dz. Oh, I forgot a integral, yeah. This is the first term minus the second term. By the way, this 1/4 I took it out there, so I won't write that again. 0 to infinity log 2 alpha e minus z dz plus 0 infinity log z e minus z dz. This thing whole squared. I just expanded this. Okay, so I'm left with 1/4 integral from 0 to infinity log squared 2 alpha times e minus z dz plus integral from 0 to infinity log squared z e minus z dz plus integral from 0 to infinity 2 log 2 alpha log z e minus z dz. This is the first term, and similarly the second one. Now again a plus b whole squared, so I get the square root of first integral log 2 alpha e minus z dz whole squared plus second term squared log z e minus z dz plus twice of first term times second term, so that becomes integral from 0 to infinity twice log 2 alpha log z e minus z dz. Okay, so now I'll see a lot of beautiful cancellations. This first term, that's log squared 2 alpha is a constant, so that comes out of the integral, and I'm left with 0 to infinity e minus z dz. But we have just evaluated that, and that equaled 1, so it's gone. And the second term, that's just f double dash at 1, which we found out earlier. And I'll keep the third term as it is, 2 log 2 alpha log z e minus z dz. This is as it is. Oh, wait, yeah, okay, that's fine. And in this term, this again log 2 comes out, log 2 alpha comes out, and integral of 0 to infinity e minus z dz you get again, so that's 1. So this term was squared plus second term is just f dash at 1, and this is the third term as it is. I'll copy that down. 2 log 2 alpha log z e minus z dz. So this is 1/4 of minus of this term and this term. They cancel out because minus I'll distribute it everywhere. So this becomes minus, this becomes minus, this becomes minus. This term, they're the same, so they cancel out. This term and this term, they are the same, so that cancels out. And I'm left with f double dash at 1 minus f dash 1 squared. And that we already calculated, that's equal to pi squared by 6. So the final answer is pi squared by 24. That's the final part.